So it's been the announced time, whatever that time may be for you. It's 10 a.m. Here in Chicago. I think it's 5 in the afternoon for our speaker in Berlin, Louis Schubert. So I'd like to welcome you all to this webinar today. I'm here, your second choice host, so I'm sorry for everyone who expected to see Andreas today. Andreas unfortunately caught COVID just a few days ago, and we wish him all the best for his recovery so that he can be back on stage soon again, but not at all. Second choice is our speaker today, Louis Schubert. Louis, I think, can rightfully claim that he is the most experienced Iris F1 user outside IRsweep because he is working on the first instrument that was ever installed outside IRsweep and was its first user. And therefore, I'm very happy that Louis is today with us. Before I give the word to Louis, let me give a very short introduction into dual-com spectroscopy, maybe the title of the webinar. So Louis will talk about protein conformational and protonation dynamics monitored by single-shot infrared spectroscopy. Now, the tool that Louis was using, among others, for those studies is the Iris F1. That is the dual-com spectrometer that we produce at IRsweep. And when we talk about the Iris F1 that you can see here in the center, we mostly talk about 4 key advantages, which are its high brightness, its high measurement speed, the high resolution, and the parallel multi-wavelengths acquisition. And I'd like to say a few words about each of them. Let me get started with the parallel multi-wavelengths measurement because that lies at the heart of the technology. So here, what you see on this screen is at the top right, the optical assembly that is usually used in our dual-com spectrometers. So as the name implies, dual-com spectrometers, we have 2 frequency comms, which are then superimposed on a beam splitter and pass through a sample and then are detected on a single pixel detector. And why we do that is shown here because, or in the center of the screen, here you can see an interferogram, which is caused by the beating of those 2 lasers. I don't want to go into details about that, but each of the lines that you can see here corresponds to an optical line which is emitted by the frequency comms. So basically you can imagine the technology to do measurements on several hundred single wavelengths at once. And we measure those somewhere in the hundreds of megahertz range. Now, that also already shows you how we can do spectroscopy with that, because you saw there were some gaps in the spectrum, and those gaps are actually caused by the absorption of the water vapor in the laboratory. And here that's quite useful because that allows us to assign actual optical frequencies to the megahertz frequencies we've seen before. And you can see with the lasers that were used here, we covered a range of roughly 1610 to 1680 wave numbers. And quite generally speaking, in dual-com spectroscopy or in QCL dual-com spectroscopy, we have more than 60 wave numbers of coverage, and we have a mode spacing of roughly 0.3 wave numbers, which results in more than 200 lines which are covered at once. Now, high brightness is the next aspect I would like to cover. High brightness is useful if you have to work with samples which are very strongly absorbing. And here, talking to a bio community, probably the most important example of a strongly absorbing sample is water. Water just absorbs a lot of light in the infrared. And if you have a lot of power, optical power to start with, it doesn't hurt so much if you lose a lot of light on the way before you get to the detector. And what is plotted here is how thick of a layer of some solvent you can use to lose no more than 99% of the light. And typically 99% of lost light is not a problem in QCL dual-com spectroscopy. And as you can see, looking at the gray line, which stands for water here, in most of the infrared, that means you can shine through more than 100 micrometers of water. And even in this 1650 wavelength range, wave number range, where water absorbs the strongest, that still means more than 20 micrometer of water that you can shine through. And that is quite a step forward as compared to other, let's say, conventional light sources. So to put that in number, typically we have output powers of more than 50 milliwatt with those QCL frequency comms, which allow us to shine through 20 to 100 micrometers of water. Then let me speak very briefly about the high resolution of the spectrometer. High resolution is a completely different field than what we're talking about today, but we have just recently shown that with those QCL frequency comms, you can do measurements of narrow lines, like for example, this methane absorption line that you can see here, which at low pressures is only in the 10 to the minus 3 wave number broadness, and its shape can be very nicely resolved with those measurements. And to put the high resolution in numbers, what we have shown, what can be achieved is step sizes on the order of 2 times 10 to the minus 4 wave numbers, and a spectral resolution, which basically we didn't really show where we get there, because we never actually measured a sample where we were limited by the instrument resolution, but it's certainly somewhere in the low 10 to the minus 4 wave number range. And then finally, there's the high speed. I don't want to say too much about the high speed because we will hear more about high speed measurements later on. But here you can see an example for fast measurement. Here, fast is on a second time scale. What we've seen here is the curing of some glue, but even faster is well possible. Typically, what is achieved with the dual-com technology that we market here is sub-microsecond time resolution on the complete spectrum that is covered by your lasers. And all of those advantages feed into a bunch of applications. I like to mention 5 of them here. One is combustion diagnostic is a big use case because, as you might know, combustion is not a very reversible process, and therefore single-shot techniques are certainly useful. Then I'd like to mention stopped flow technique for everyone out there who's interested in solution-based chemistry. Stopped flow, you can mix chemicals very quickly and then study microsecond reactions in those solvents. Then I'd also like to mention spectroelectrochemistry, because that is also an example where things actually happen on the micro to millisecond time range, but so far it was difficult to see this in the infrared, and we're very happy that we had some users who developed spectroelectrochemistry with our fast infrared spectrometer. And there's the high resolution field to be mentioned for every one of you who's interested in line shapes and line parameters. There our spectrometer has things to add. But for today, the main topic, of course, is protein dynamics, and I'm not going to say anything about that because we have an expert for protein dynamics here. And with this, I think I'd like to give the word to Luis, who will talk about protein conformational and protonation dynamics monitored by single-shot infrared spectroscopy.
All right. So thank you, Markus, for the introduction. Sharing now my slides. Yeah, thank you for the introduction, and welcome also from my side, from Berlin, where it's very warm outside. But I think that's also the case for America right now. Yeah, I'm talking about protein dynamics now. And yeah, let's just dive into the topic. A little introduction to spectroscopy on proteins. So here I show you a crystal structure of a membrane protein. It's bacteriorhodopsin. It consists of roughly 250 amino acids. And I show it to you in this messy stick representation to show you that there are many, many bonds which can all vibrate and give rise to signals in the infrared. And if you record such a FTIR spectrum of a protein, you see overlay of all these vibrations. So it's really hard to get a lot of meaningful information from this, but the trick we apply is different spectroscopy. So what we can do is we can record a spectrum of the protein in its resting state, and then we can trigger the reaction of the protein and record a spectrum, or in the best case, a series of spectra in a time-resolved manner of the protein while it's working, while it's doing its reaction. If we then calculate the difference of these two spectra, we end up with a different spectrum. And by this kind of nice trick, we basically silence out all the vibrations which do not change upon applying the trigger. So this is a very convenient way to learn something about the functional mechanism of the protein. You are still left with quite many vibrations, but these you can now assign to vibrations which have changed upon applying the trigger. And you can learn something about single amino acids, the whole protein, or chromophore vibrations whatsoever you're looking at. In the most elegant way, you're looking at a light activatable protein, and then you can just use a pulse of light to trigger your reaction. But there are also other ways like temperature jump or pH jump, or whatever your system you're looking at, you need a different trigger. In our group, we are mostly looking at light activatable systems, photoreceptors. And in this context, we are interested in a variety of reactions. For example, the photoisomerization or the thermal isomerization of the cofactor taking place on different timescales as indicated here. But also very important, we are looking at the protein conformational changes, so overall structural changes, and maybe most importantly, looking at proton transfer reactions. So depending on what reactions you want to observe, you need different methods. The workhorses in the field have always been FTIR spectroscopy, and here with step scan and rapid scan FTIR, you can cover the time range from sub-microseconds up to the second range. If you want to look at faster processes, you can use pump-probe spectroscopy, but that's not the expertise of our group. We are more looking at the slower processes. Therefore, we developed a few years ago a scanning type spectrometer based on an external cavity quantum cascade laser, which covers the time range from tens of nanoseconds up to hundreds of milliseconds or even seconds. And as Markus said in the beginning, we were the first customers of the IRsF1 dual comb spectrometer, and we are using this spectrometer to cover the time range from also sub-microseconds to tens of milliseconds routinely, but with the new measurement mode, now it's also possible to go up to the second time range. So a little introduction on the sample I will be talking about today. I think to some of you it should be known. It's bacteriorhodopsin. It's a light-driven proton pump, as shown in this little animation here. Upon absorption of light, it pumps protons across the cell membrane, so it generates a proton gradient. And this proton gradient can then be used by the ATP synthase to convert this gradient into chemical energy in the form of ATP. Now this vectorial proton transfer is achieved by a fast photo cycle of the protein. So this is shown in this schematic here. BR in its ground state absorbs a photon. The ultra-fast photoisomerization takes place, and then a series of thermal reactions take place. And the nice thing about this photocycle is that it's actually cyclic. So after the last reaction, BR is back in its initial state. So we can repeat this photocycle over and over again and average and do methods such as step scan and where per definition we need to have several excitations. So we need a strictly repetitive system to study or to do step scan FTIR. If we succeed with a step scan experiment, we get relatively broadband spectra from the microsecond to the millisecond range, where we learn quite a lot about the protein, looking at chromophore vibrations, as shown here, which are usually quite big as compared to the protein signals here in the carbonyl region, which report on protonation states of carboxylic residues. And we can also look at the amide-1 region here to look at structural changes of the protein. But as I said, for step scan, we need strictly repetitive systems. Now, what if we want to study a non-repetitive system? So, for example, if we want to look at the light-insensitive protein, or we would like to look at the irreversible chemical reaction where just a educt is transformed into a product, or we look at a maybe photosensitive protein, but it might degrade over time. So as for example with bovine rhodopsin, or the rhodopsin we have in our eyes, where the retinal chromophore drops out of the protein after excitation, or you use a caged compound which is consumed with every laser shot. In that case, it's good to have a technique which allows you to do single shot experiments. And with single shot experiments, it's a little dramatic animation. That's what we mean here. You have only one shot or one trigger you can apply to the system, and you need a method which gives you a high enough signal to noise ratio to study your reaction with only one average. So that is what this talk is about, but we were not the first ones who did this, but the group of Tillmann-Kottke, together with the IRsweep, did already a single shot study on BR, looking at chromophore vibrations, and they compared it to their established method of step scan FTIR. Now we took this method a little bit further and wanted to compare it to our home build setup using an external cavity QCL. And this data I'm showing today is now basically published in Journal of Chemical Physics, and I will guide you through the main findings we have. But first of all, I give a very brief introduction on the setups. So as Markus introduced you already to dual comb spectroscopy, I want to keep it brief. But the very important thing is here that we probe several frequencies over time at the same time. So we measure spectra, consecutive spectra, while with the external cavity QCL, we can only measure one frequency at a time. So in the ECQCL, it uses a grating with which you select a certain frequency, you tune to this frequency, you can excite your reaction, and you can measure the transient. And if you want to retrieve spectral information, you need to tune to the next frequency and repeat the experiment over and over again. And in dual comb, you can measure roughly 60 wave numbers in parallel, which is a great benefit over the external cavity QCL. However, usually the tuning range of ECQCLs is a bit bigger than the bandwidth of the dual comb system. Another advantage of the ECQCL is the time range you can cover. So we have in our setup a time resolution of roughly 10 nanoseconds, and we can go up to 100 of milliseconds, and if we're lucky, even up to seconds. While in the dual comb system, in the time resolved mode, you're limited from microseconds and maybe sub-microseconds up to tens of milliseconds these days. But there's now a new method where you can extend the time range up to the second range. Here's a little photograph of our ECQCL setup. Since this is home built, I thought this is interesting. So here are two QCLs, and there's another QCL outside here, which are then directed through an aperture which attenuates the beam and is then directed to the sample. and focused on the detector, and the green line here indicates where the excitation beam hits the sample. So that's also a fairly, wouldn't say easy setup, and my colleague who built this thing would be a bit annoyed by this, but it's nothing fancy, let's say that. So now let's look at the data. We looked at conformational dynamics of the protein and protonation dynamics, and let's start with the conformational dynamics over here. So in the first study, we allowed for 3,000 shots, and these 3,000 come from the fact that we wanted to look at the spectral range from 1680 to 1620 inverse centimeters, and with a spacing of 1 inverse centimeter. So we measured 60 kinetic traces, and every trace we averaged over 50 excitations. We then get a nice 3D data set where we can extract spectra at certain times, and also specific kinetics over here. So we get nice data with high signal to noise ratio as we expected, and this matches the time resolved FTIR data, which is well known for bacteriorhodopsin. If we do the same with the dual comb setup, where we now just measure 3,000 shots and average them, the data match nicely, show the same bands basically, but here you see that the range, the time range of the dual comb system is a bit limited as compared to the ECQCL. So if you have a repetitive system, in that case, the ECQCL is here beneficial. But as I said, now these methods are not about looking at the repetitive systems. So we restricted ourselves to a single shot. And here I show you data now exclusively from the dual comb spectrometer. Here in the top part, I show you the data achieved with 3,000 shots. It's the same data I showed you on the slide before. And now I compare this to our single shot experiments. So here you see the kinetic trace at the 1670 inverse centimeters. This band is assigned to a amide-1 change of the protein. It reaches its maximum at around 3 milliseconds. And you can see that the green trace, this is the kinetic obtained by a single shot experiment, has very high signal to noise ratio here in the end. So you can really see that this trace shows the same transient as in the multiple shot experiment. Of course, if you do 10 shots and average them, your signal to noise gets higher. And the gray shading shows the standard deviation of the 10 individual single shot experiments. So this shows quite nicely that you see the same. So you do not need 3,000 shots to average. A single shot or 10 shots are sufficient to extract the same kinetic information. Now, the good thing about dual comb spectroscopy is now that even with single shots, we also get spectra. So here I plot the single shot spectra and the 10 shot spectra and the standard deviation. Again, that's the same color code as here. And you can see nicely in the 5 millisecond spectrum that all spectral features are resembled in the single shot experiment. In the 300 microsecond spectra, the spectrum looks much noisier. This is due to the fact that the noise is reduced in the 5 millisecond spectrum because we do a logarithmic averaging on the time axis. So the noise here in the earlier times is significantly higher than in the later times. However, still 10 shots are sufficient to extract the same spectral features as from a 3,000 shot experiment. And I think in most cases, you can prepare maybe a few samples and average some maybe 5 or 10 single shots to increase your signal to noise. So you can also access the microsecond time range with single shot experiments in that spectral range. Now, what if we allow the ECQCL only a single excitation? We can do so, but if we do so, we have to select one frequency and we are limited to this. So we can get a kinetic trace with a single shot. So here's a single shot kinetic acquired with the ECQCL at 1670. This has a very nice signal to noise ratio for a single shot. We're very satisfied with this. if you compare this to the dual comb SingleShot Kinetic, the SNR in the ECQCL is better than in the dual comb, because there's simply more light on just one frequency, and in the dual comb, the emission of the QCL is distributed over several frequencies. That's why the noise is higher in the dual comb. But now the great benefit of dual comb is, as I said already, we get spectra even with a single shot, as shown here. Not only that it's nice to have spectra, of course, it's also good if you want to apply some data analysis tools, such as SVD or global analysis or LDA, as we did here. This is really nice. If you have spectrotemporal data, you can improve your data quality further if you do some fitting and data processing. A colleague of mine wrote a Python-based script where you can do LDA, SVD, and global analysis, and this is available here on GitHub. So if you want to try it out, feel free to do so. It's very handy to use together with the IRsweep scripts they provide also in Python. So next, looking at BR, of course, protonation dynamics are the most important reactions taking place here. So we can look at protonation events if we study the carbonyl vibration of carboxylic residues. As shown here, they are sensitive to the protonation state of this amino acid. And in BR, the protonation transfer is well studied by StepScan FTIR. And one key reaction is the protonation of aspartic acid 85 by the retinal Schiff base. This is indicated here with the number 1. And in FTIR, we know that the protonation of D85 is shown by this positive band here, located at around 1762 inverse centimeters upon formation of the M intermediate at 300 microseconds. And then we know that the structural environment of the D85 is a bit altered in the later intermediate, so this band shifts by a few wave numbers to lower frequencies. And now we used again our BR sample and wanted to investigate this reaction with dual comb spectroscopy. Again, here these signals are usually much smaller than chromophore vibrations or amide vibrations, so a method with high SNR is much needed in this spectral range. And here I show the single shot experiment in that spectral range. It's again the same color code as before. So the colored one is the single shot spectrum, black is 10 shots, and the standard deviation in gray. And I think this shows quite nicely that a single shot is sufficient to really see the protonation of this aspartic acid in BR. You can see also then at the later times the shift of this band towards lower frequencies. So our method is really, the dual comb spectroscopy is suited to get nice spectrotemporal information in that spectral range and study proton transfer reactions. Now to maybe more illustrate a way how one could combine these two methods, let's look at the isotope effects. So if you replace water by D2O in bacterial rhodopsin and you exchange the dissociable protons by deuterons, you will observe the kinetic isotope effect on proton transfer reaction, which means that a proton transfer is slowed down when a deuteron is transferred instead of a proton. And this is again nicely shown by a single shot experiment with the ECQCL. So if you probe this kinetic here, you have this kinetic trace in water, and if you do it now in D2O, this reaction becomes slower, and this is resolved with a single shot. Same is true for the dual comb data, which resolved this slowing down of this reaction. However, now here you have also the spectral information where you see that this band also shifts upon the vibrational isotope effect. And I think this kind of nicely illustrates how you could combine this, because you cannot do the ECQCL single shot experiment without the knowledge that this band shifts by roughly 10 inverse centimeters. So I think it's a nice experiment to do first your spectro-temporal characterization with the dual comb setup, see where bands are located and shifted probably over time or upon HD exchange or pH change whatsoever. And then if you have located this band at a certain time and you're interested in higher time resolution data, then you could use the ECQCL to tune to that frequency and measure a single frequency at that position and have a bit more information with respect to time resolution. So with this, I come to a short summary of the two methods. So I think we could show that with this high emission power of the QCLs, we are able to perform single shot experiments in the amide-1 region as well as in the carbonyl region to study proton transfer. The ECQCL has a higher time resolution, but the dual comb setup has spectral information in a single shot, which is a great benefit. We think these two methods can be combined to study irreversible reactions in the future, and I think that's a powerful tool. And yeah, where to go from here? Obviously, should not continue measuring BR all over again, but continue in measuring non-repetitive reactions. And here, I think one needs to have clever triggering systems, because if your trigger is not light, then you need maybe a rapid mixing tool or a temperature jump, or you use cage compounds, as the Gerwert group showed with IRsweep already together. And by this, really start studying not just photoreceptors, but other interesting enzymes and proteins. Another thing where I believe the QCL-based spectroscopy is very useful is in the combination with crystallography, time-resolved crystallography, where you can determine the crystal structure of a protein at a certain point in time after it has been excited by a visible laser. And yeah, if you do not know a lot about the reaction of the protein in advance, then you're fishing in the blind and need to have a lot of crystals to study by chance a good intermediate. But if you do in advanced time-resolved molecular spectroscopy, and here especially maybe QCL-based spectroscopy has some benefits, you can tell the crystallographers where large structural changes or protonation events take place, and then they can adjust their experiments to find the correct points in time to determine the crystal structure. And with this, I'm already at the end. I want to thank you first of all for your attention, and of course Joachim Eberle, who made all this possible, and Victor, with whom I had a lot of discussions about methods and data treatment. It was very helpful. Pitt, who is building and maintaining our ECQCL setups, and David, who wrote the Python toolbox, which is available. So if you have questions about this toolbox, just send me an email. I'm happy to help. And of course, some financial support. And yeah, with this, I'm happy to take questions.
Great, Luis. Thank you very much for this talk. Quickly switch back. So we don't forget that we see you. And I think we've already got one question here in the Q&A from Edward Kukla, who asks, I noticed that the peaks of the bacterial rhodopsin are shaded gray. Does this indicate that the absorbance to concentration is calculated from the integration of the peak, the area, rather than simple peak height? Does this reduce the effect of noise in the calculations?
I don't know if I quite get the question, but I think it's a different spectrum, so we do not calculate here the absorbance from a concentration. The gray shaded area is the standard deviation of 10 single shot experiments. So we do 10 single shot experiments, and they have slightly different signal intensities, and that's why there is some deviation.
Yeah, I think what he's
gray
referring
area.
to is your FTIR measurement where there were where the peaks were shaded, were filled out gray. And,
no, this is just for aesthetics.
That's just for aesthetic. You typically don't really calculate any concentrations, right?
Yes.
So,
yes.
Then we have a question from John Kenneth, which is, what are the typical delta A's you record in the single shot regime?
Yeah, so it's a good question. I had a scale bar in the spectra, but it's probably hard to see. So it's some milli-OD. So I think more than 1 milli-OD, between 1 and 5 milli-OD. So we have quite a lot of BR in the beam path and excited with a bit more laser energy, but not too much.
And if you add some lifetime density analysis or other methods, do you think you can get to see lower absorptions even in single shot measurements?
Yes, but I think it's always worth spending time on making a good sample and having quite big signals rather than in the end spend too much time on data massaging. But yeah, I think, I mean, BR gives nice and big signals, but we can also measure with slightly smaller signals. But of course, if you're going below 1 milli-OD, then in a single shot experiment, it's going to be hard.
I maybe also have a question more towards the biology part. Somehow bacteriorhodopsin is this very nicely reproducible thing, and then there's those other rhodopsins which you seem to be interested in, which are not at all repeatable. What happened? I mean, for me as a non-biologist, it looks like the same thing. It's this membrane protein pumps protons. Why are they all of a sudden so badly reproducible?
Well, I think, I mean, first of all, the sample production can be much harder for other proteins than it is for BR. So there's not that much available, so you cannot play around that much. Yeah, BR is very stable. You can leave it on the bench for weeks and years and nothing happens. Other proteins degrade over time, are very sensitive to hydration levels whatsoever. So I think everyone who works with biological samples knows that it's sometimes hard to handle the sample.
Okay. There was actually also a question in the chat, which I directly answered in the chat, but it might be interesting to everyone. The question was, will there be a recording available later for me to watch on demand? And the answer is yes. So the webinar was recorded and it will be available from our website within a few days, I would say. And of course, what you also see from the slide here, if you have questions later on, you can always contact us directly on the channels that were there all the time, which is our office in Switzerland with the Swiss phone number and the sales at IRsweep website, and very newly also the new office which was opened in Chicago. So I am hosting today out of Chicago because I'm building up our new North America office. So for all of the North American spectroscopy users which are here today, I'll be more than happy to answer any questions that you have, and you can reach me under this US phone number or the US sales@irsweep.com website email address.